All right, what's going on, everybody? We are here on Tuesday of week 10. We are going to look today at throwing some calculus into our parametric curve stuff that we looked at in the last video. In the last video, we introduced the idea of parametric curves. Parametric curves are curves that are parameterized by an additional variable that is helping us describe what values we'll achieve for x and for y. It is typically, in my opinion, and in lots of people's opinions, most convenient to think of our parameterization variable as time, at least in our simple settings. Hopefully, all of you just become lifetime mathematicians, in which case you will see lots of scenarios in which parameterization happens with things other than time and with more than one parameterizing variable, t. But I think in our simple, getting comfortable situations right here, we want to think that time controls our XY location. So it's always good to kind of have for yourself an example to think about your parametric equations. And I'm always picturing the trajectory of either like a fly flying around the room or just a particle in space, and that the XY coordinates are determined based on time, which is a very sensible thing for us to think. So we introduced all the concepts associated with thinking about parametric curves, and importantly introduced our looking at Desmos with parametric curves, since it can do that very well for us. So now today what we want to say is, well, since those are curves in space, it would be pretty cool if we could do all algebra things with those curves. And so when I say all algebra things, that was a terrible sentence right there. All calculus things. And when I say all calculus things, what I mean is we want to be able to compute derivatives. We want to be able to compute integrals. If we can compute integrals, then we want to be able to do sort of the more special case integral things, not just finding area underneath the curve, but also finding things like arc length, surface area. What we're going to see today is that all of our formulas just need to be modified slightly, but otherwise they're going to, in a sense, retain their structure as to how do we arrive at the appropriate parametric forms of all of these computations here. So we're going to look at all four of these things here today, I guess, sort of. We'll go through these kind of a little bit quickly, but the point is that I think that the more important part of this section is the deriving of the formulas. You already know what to do and how to use all of the formulas that we're going to look at today. You just need the formulas. Really, it's like where do they come from, and understanding why they're formed that way is the important thing. And actually, I'm going to show you too. I've been getting a little bit of variable confusion in one of my formulas. I'll show you also a mistake that I've made multiple times in prepping for today, that I'm just going to go ahead and make today as well, just so that we can kind of see why it occurred. So again, this is like everything we've done in calculus right here, and we just want to say, well, this should be able to apply to parametric curves, not just y equals f of x curves. So kind of our yeah, okay, all right, hit that all the way down there. So we already know how to do all these things for equations of the form y equals f of x, or x equals f of y. We've done a lot of our things saying we can rotate our solids of revolution around the x-axis or the y-axis, right? So sometimes we solve these for different variables, but the important thing that we've always been able to do is to form a direct, explicit relationship between x and y, a single equation with just x and y, where we can solve for either x or y. What we want to do is just modify all of our existing ideas to fit parametric equations of the form x equals f of t, y equals g of t. So one thing that is somewhat unfortunately important for today is remembering that f is always associated with our x information, and that g is always associated with our y information here. I'm going to keep on constantly reminding you of that, but again, in my preparation for today, this has been one of those things where I've needed to like flip back in my notes and be like, wait, F is X stuff, right? Yeah, okay. And kind of talk myself back into that. So just kind of realize that just like this is a pretty generic naming convention. X comes before Y, F comes before G. I don't know. There we go. Keep that straight. They're both sequential in the alphabet like that. So the key to doing all of this, everything that's going to happen today, is that we want to replace derivatives and differentials based on single replacement rule. FT is X stuff. Got it. Cool. Yeah, there you go. You're down. And there you go. Good call, copy, gopher. You really only have to remember one pair, and you automatically, by default, remember the other pair right there. So X is F stuff right there. So let's start with our beginning things right here. Derivatives of parametric curves. What we'd like to be able to do is to find the slope of any curve, not just curves that are in our y equals f of x format, but maybe in parametric format instead. Slope is still going to be defined for us as dy dx. It's still our rate of change of y divided by our rate of change of x, if we're thinking delta y over delta x, right? But the dilemma here is that it's not necessarily guaranteed that we will be able to explicitly solve for y in terms of x. Now, I am going to start with us looking at a scenario in which we did manage to do that yesterday, but just to kind of like help reinforce that this does happen occasionally. In our last video, we did see this one scenario where we can explicitly rewrite our parameterization in function form. In general, this is always super duper duper easy whenever this is your first parameterization. This is literally saying to me, this is almost like a false parameterization here because this literally just said rewrite x as t and nothing else changed. And so this is really just y equals x squared is all that we're seeing right there. So this is about the lamest parameterization in all of history right there. But this is just kind of showing the example. Yeah, sometimes you get a parameterization x and y of t, and you're able to rewrite it as just a y equals f of x scenario right there. And and I just said a bad thing right there. When I said y equals f of x, I didn't mean the f that we're referring to as in terms of x. As you're going to see when I scroll down here, we're going to reference a capital F today to mean our function form as opposed to our parameterization form. I kind of hate the use of the lowercase and the uppercase f's in general. I think those get confusing since I'm a very verbal person, but I didn't find too terribly much confusion with doing the replacements we need to do today. So stick with this. We won't see this capital F too much right here. So here's really our deal. It's not guaranteed that we personally are going to be able to do this. But what I think is useful for you to imagine is that somewhere out in the universe, maybe there's some outrageous algebraic technique that we haven't come up with that maybe would allow us to do something like this, even if it wasn't in very convenient form. So our sort of imagining part that's going on here is imagine that we're capable of doing this, rewriting our parametric form x equals f of t, y equals g of t into some function form where y is a function of x. If that were the case, then we would still be interested in, like we said, finding dy dx. But now, based on the way that we've phrased this, we can now phrase this slightly differently. Dy dx is this capital F prime of x, because we're saying that capital F of x is exactly how we're defining the y functions. This says take the derivative of y with respect to x, right? So here's how we're going to do this. Let's just start from this imagined y equals f of x that we probably can't find. And let's use the fact that we know that x of t is, or x is f of t, y is g of t, to help find an alternate form for that. So here's what we're going to do. First, so we're going to start with just our generic statement. This is our imagined thing that we can't find. In this line right here, all we said was that y is g of t and that x is f of t, right? That was just how we defined our parameterization. So all I did is subbed in for x f of t and for y g of t. Our goal here was to find f prime of x. So what I'm going to do is I'm now going to take my derivative of both sides with respect to t. Right? Now, when I take the derivative on the left, the derivative of a function of t is just the derivative of the function of t, right? This is a function of t, so I just got the derivative. So that, nothing exciting happened right there. Notice over here, we get the chain rule right here. Right? So the derivative of f of t, and if you're just listening to my words, that's capital F of lowercase f of t right there. The chain rule says take the derivative of the outside function, that's the f, leave the inside parts alone, times the derivative of the inside function. Now we go back to, let's say, replace x with f of t. Oops. F of t with x. Notice here, the only thing that changed is we just made our x of t swap go back down to being actually x right there. And now notice we did exactly what we set out to do. We found f prime of x. Seriously, and you're going to see some more algebra today where you're going to be like, oh, holy cow. And it's cool. And it's like, oh, that stuff worked out nicely. And so, and I also just want to say that, like, the thing that my big takeaway from all this stuff is being like, oh, so if I just play around with things, I can find the quantity I want. Like, I didn't really need guidance for this. I just started hitting some terms with some things that I thought that belonged with it and got out my beaten stick and started solving. And oh, what do you know? We found exactly what we wanted right here. So now I just do a little bit of a derivative right here and I get this f prime of x. And so what this is really saying to me in alternate form, now remember, capital F prime of x, that's what we said was dy dx. So that's my left-hand side. F prime of t, this is the derivative of x stuff with respect to t. That's dx dt divided by dy dt. And so you should notice that this agrees with fraction cancellation rules. Right? In this scenario, you would do dx dt if this was actually fractions, which these aren't fractions, but it happens so that they work out like fractions. If this were a fraction divided by a fraction, then the way that we would compute that would be by flipping the bottom fraction up to the top and multiplying. So you would get dx dt times dt dy. The dt's would cancel, and you'd be left with that dy dx right there, right? And so yeah, that's what I thought. Okay, I'm being crazy right here. Why do I have my... Oh my gosh. Okay, sorry. I just got led astray right here real quick. Notice that I did my algebra dumb and so notice over here I have y on top and x on bottom. Here I have x on top and y on bottom, which is backwards, and I'm sitting here saying it out loud and I'm like, and that gives dy dx equals dx dy. That's not right there. I got this a little bit backwards. Notice that what I did over here is I wrote this line to this line wrong right here. I should have been dividing by f prime of t on both sides, but here I flipped my fraction. I've got this fraction upside down right here. So this should have been just following my algebra, right? That was just divide both sides by f prime of t, and I did it backwards right there. So okay, so there we go. So that's now fixed, and so now I can go ahead and fix this statement right here. Okay, there we go. Fixed it. We're now good right here. It is the dy dt on top, the dx dt on bottom right there. Okay, small algebra error. And isn't that nice today? As it's been going for weeks and weeks and weeks, more likely to make algebra mistakes than calculus mistakes. I think that's sort of the funny part about this class, is that the calculus is very hard. The algebra is always what's at my edge of my abilities right here. So the point is here, we now have a way to say, listen, what I would want to do, what I would hope to be able to do is if I wanted to find dy dx from a parametric set of equations, is to combine the equations into a function form, then take its derivative like I'm used to. But the point is, we probably can't do that. We probably can't get this guy. But now we can see that even though we can't directly get that capital F function, we can still find the capital F function's derivative in terms of our parametric equations right here, meaning it's okay if we can't get to here. It's okay if all we have is x of t and y of t, and we can't get to here. In most parametric equations, that's true. We can still find our derivative by just taking the individual derivatives with respect to t and taking their ratio. So let's go ahead and look at an example that utilizes this here. So this will be kind of our final formation right here of how we think about derivatives with parametric form right there. So we'll come back and use that formula. So let's look at this parametric curve right here. X of t is t squared, y of t is t cubed minus 2t. This is example 1 in the book. I'm being a little bit lame right here, but I'm going to phrase this question a little bit differently. And the book does a bunch of other parts that I'm going to kind of combine some parts and eliminated some parts right here. Yeah, calculus is hard to do right. Algebra is easy to do wrong. I agree with that, and we're going to see, by the way, that I make some algebra mistakes coming up here that are easy to do wrong. There's just so much algebra that really happens that it's really like, by now we're doing like 50 algebra steps in one, and so yes, it only takes one mistake for us to be off, whereas the calculus ideas, I think, are just bigger ideas. So let's show that this parametric curve intersects itself at a point. And here's what I'm kind of thinking to myself. If a curve ever does something and it's moving along and then it intersects itself at a point, the thing that you should notice that's a little bit weird here is that at all of the points on this curve, I could drop a tangent line, right? We could drop a tangent line there. We could drop a tangent line there. We could drop a tangent line there that looks like it's horizontal. We could drop another tangent line. You know, all these places have tangent lines, but the weird thing is that there's two different tangent lines that occur at that one point, right? So it seems to me like one way that we could confirm that a function, that a parametric curve crosses over itself is to identify that it has two different derivatives at one location. That makes sense, right? There's one xy location, the point of intersection, but it has two different tangent lines, one for when it was going up the swoop, one for when it's going down the swoop right there. So let's go ahead and see that we can show that it has this intersection at 3, 0 by showing those two unique derivative values at that location there. So as I shouted at you guys last class, every parametric situation you are ever in, you should graph first to make sure that you have the appropriate visual intuition. Graphing these by hand is hard, and we're not confident with the functions that we're looking at here. So let's go ahead and pop over to Desmos and do that here. And so we were looking at the equations t squared, that was our first equation, comma, what else were we looking at here? T cubed minus 2t. T cubed minus 2t. And it's always going to give me from 0 to 1 as the default bounds. My typical move here is to extend this one out as far as it shows on the screen. So just going to 10. Oh, you're not seeing quite exactly what I'm seeing right here. Let me zoom out a little bit and drag this over. So already this thing's shooting off the screen for me. I can see even if I drag it up there, like this is plenty far enough for me to be able to see what's going on here. I am a little bit more interested in the nearby local behavior here, though. So apparently we also want to look at some backwards time parts right here. I'm just suspicious, does this go anywhere else? And ooh, by adding in some more, it looks like it was all those other parts that were out there, right? So in fact, by the way, maybe this is actually a practical thing for us to do right here. To see that there's sort of like forwards time and backwards time parts here. Going from -10 to 0 gives us those other pieces that are right there. So sometimes it's useful to look at just the forwards time parts and just the backwards time parts to kind of just see where that distinction lies. So it looks to me like it's got to be the case that at time 0, we're at 0, 0. I can easily confirm that by plugging in 0 for t to see that the origin is truly our starting spot. So it looks like we can either go forwards in time and we will hit this location at 2, 0, or we can go backwards in time and we will hit this location here at, oh, sorry, that shouldn't be 2, 0. That's because I should have put a 3 right there. And there should be a 3 right there. Sorry, I just copied the problem in wrong right there. So it does look like we're getting this intersection at 3, 0 like we thought, although as we saw last video, Desmos won't click on this to tell me that point because Desmos is a little less confident in his parametric curves. I am hoping, by the way, in my wildest dreams, there's a whole bunch of super nerds that are out there. Desmos is really made for like algebra and trig. I want Desmos to do things like show me solids of revolution. I want it to be better with parametric curves. I want it to have built-in derivatives and integral stuff. I want it to be better at shading certain regions of the graph without having to give intervals. I am in my wildest dreams. Sometimes I wake up in the morning and when I like don't want to get out of bed, it's because my last 1 hour of dreaming was that Desmos Calculus Edition just came out and that teaching is now half as hard as it was for me before. One day you're going to see that your kids are going to have a much, much better version of Desmos than we have here. So the point is we're looking at this graph. We see it's got these two lines right here. I'm expecting to find two tangents right here, two slopes, one that's positive and one that's negative right here. Because we do have this intersection. There are two different possible things that could be occurring at that location of 3, 0. So let's go back and see if we can kind of identify where some of this stuff is actually happening here. So we want to find these, a derivative right here, right? So we're looking to find a general derivative, and then we want to evaluate that derivative at the appropriate time. So let's find a general derivative. want to say specified, at the time t of interest. So if we want to find dy dt in this case, we just saw that it's pretty simple. Nope, that's wrong. If we wanted to find dy dx in this case, the slope of the curve at any given point, that should be dy dt over dx dt. And those are pretty dang easy because these are polynomial parts. The derivative of y with respect to t is 3t squared minus 2. Oh my gosh, that's why I copied it right there. There we go. Yeah, so by the way, and so notice, so the question I'm getting right here is, couldn't we substitute t into y of t by square rooting x of t? And maybe let's go ahead and do the problem the way that you're talking about after we do this to verify that we're going to get the correct answer right here. I do, oh, I'm so glad that you brought that up. So what you should be thinking to yourself, though, is if we then take that derivative, the derivative of a function is going to be another function. But if it's a function, how can we get two outputs for one input? And we're going to see the dilemma with exactly what you just said right there. So super good question, pardon, Reed. And we're going to do that after we do this now that you brought that up right there. Good point right there. So my annoyance with myself right now is I've made this dumb little typo in here several times. Now I'm going to finally fix it. So this should be 3t squared minus 3. Okay, I'm done inside of that. We're good now. Okay, 3t squared minus 3. All divided by dx dt is just going to be 2t right there, right? So what I'm looking at here is when I go ahead and do this division here, it looks like I'm getting here 3 halves t minus 3 halves times 1 over t, also known as 3 halves t minus 1 over t. So it looks like we found the derivative of dy dx in terms of t, but notice that I know the xy location. We need the times that's there, because time is the parameter of interest for dy dx, right? So we have that location of 3, 0, but we need the times, right? So all we really need to do here is identify that's x stuff, that's y stuff here. So I could do something like, say, x equals 3 and x equals t squared means that 3 equals t squared, and that's going to tell me that t is going to be at plus or minus the square root of 3. And by the way, notice that we alternatively could have done, what? How do I scroll and it moves stuff? That doesn't even make sense. That doesn't even make sense. How did that even happen? You're about to do it again. Stop doing weird stuff here. Okay. So notice that we also alternatively could have done, or y equals 0, y equals 3t cubed minus, right? 3t cubed, or no, t cubed minus 3t. And that would tell me that 0 equals t cubed minus 3t. And that would tell me that 0 equals t times t squared minus 3. This gives t equals 0 or t equals plus or minus root 3, which is just what we got before. What we'll find is that when we plug in time 0, that does not give us the appropriate x value. T equals 0 disagrees with x. So it looks like we've found that the location of 3, 0 is visited at times t equals plus or minus root 3. And therefore we can then say dy dx evaluated at t equals positive root 3 is going to be our, what equation did we just get up here? 3 halves t minus 1 over t. And that's going to give me root 3 minus 1 over root 3. 1 over root 3 is root 3 over 3. Let's do it like this. Well, okay, whatever. I'm not going to go ahead and clean that up right there. The point is we could then do dy dt or dy dx evaluated at, holy cow, what am I writing over there? I'm writing everything out of order, weird places. Okay, okay. Dy dx at t equals negative root 3, and we're going to get here at 3 halves negative root 3 plus 1 over root 3 right there. And so we're going to get a bit of a different result. You should notice that this one right here is our negative slope and that this one right here is our positive slope. I know that because root 3 has to be bigger than 1 over root 3. And I know that because here, this negative is going to be bigger than this positive right there. So the negative overtakes this guy right there. So it looks like we did find two slopes at one location. Now, the question was, couldn't we have just solved That's the other question right here. Couldn't we have just done this? Did I typo something there? I did typo something. You're right there, Coffee Gopher. Coffee Gopher. I should have a dy dx right here. That was correct. We are looking at the general derivative overall. Yep, you're totally right there. I'm probably going to make more of those here today. So that was a general derivative of the curve at a time. Derivative of the curve at a time. And we needed the partial derivatives with respect to t to compute that dy dx right there. You're totally right. You got it. So couldn't we have just solved this dang thing? Well, how would this work here? X is t squared, y is t cubed minus 3t. So the suggestion here is I definitely think solving x for t and plugging it in there is easier than solving y for t and plugging it in there because I don't know how to solve a cubic. But notice the thing that's going to happen right away. If I try and solve for t, what am I going to get? I'm not just getting square root of x, I'm getting plus or minus the square root of x. And so that's going to lead me to two different y equations here, where we're going to get y is the positive square root of x cubed minus 3 root x. Or I'm going to get y, and this is going to be for when t is greater than 0. Alternatively, I could get y equals the negative square root of x cubed minus, I guess this would end up being plus 3 root x. And this would be appropriate because this was for our times being negative root x, so times are negative. This is when times are less than 0. And so we can go and confirm back in Desmos that these equations are legit right here. Let's just do that real quick. So what is that? Root x minus 3 root x. And there it is. And you can see that our purple curve is, in fact, the positive parts. Notice that the blue is where the times are positive, and the purple is exactly overlaying that guy. And that's exactly where we were seeing the positive results back over here. So the answer to your question is yes. It looks like in a sense we could, but we now have two different equations that we have to deal with rather than one different equation that we have to deal with. Now we need to be able to solve, now we need to take derivatives here, which is going to take, okay, the derivatives here aren't going to be too insane for that guy, right? And then, let's see here, what else? Yeah, I guess we can go ahead and find a dy dx here. And notice here, we would then be plugging back in the xy coordinates. But again, in here, we got two branches. And again, what you might be able to picture for yourself is that some parametric functions have graphs that do stuff like this. And notice here, we're going to get like an infinite number of intersections that are all at the origin that are right there. And then things are going to get a lot more difficult for us to describe because we have to have all of these different decompositions out there. So again, the point is here we could have technically, and you would technically get the correct right answer because you would have two different derivatives for the two different pieces of curve, but they'd both be at the location 3, 0. So I think our kind of bigger idea right here is just that this will work whether you can actually do that solving or not. In this case, we technically could have. I think it's more work because it's going to then generate two different sets of equations. But the point here is that this is even more powerful of a technique than that. Even if we were really stuck and we couldn't have done it, this still would have gotten us there. Even if this was x to the fifth plus 2 and our x cubed equation, and we couldn't solve either to sub into the other, this still would have worked out this way to pan out here. So, but I really appreciate that question because I do think a lot of times I see, oh, this is in a scenario I'm not comfortable with. Can I get this back into a scenario I am comfortable with, our function formation? And the answer kind of was yeah in this scenario. We technically could have. So I don't think that that's a bad idea. Obviously, we're just trying to show off a new technique here. So that's a good thought, and I'm a huge fan of people doing problems multiple different ways because it really helps say I actually am certain that I know what I was seeing out there because I was able to confirm it from multiple different angles. And we're going to do some more of that coming up here in a minute. Nice. Yeah, exactly. The first method keeps it all contained in one expression instead of you having to deal with branches. I think that's a good benefit, but this would work right here. So we just did derivatives right there. And I'm just going to say real quick, the book also discusses second derivatives, which I know that you guys know how to just take another derivative of a first, so I'm not worried about you figuring that part out. The book also talks about finding tangent line equations. I know that you guys could have computed the number that's associated with each of these guys right here and thrown it into a point slope form with the 0.30, and you'd have two equations of lines right here that you could satisfyingly graph on that graph. I'm not going to go back and talk Calc 1 stuff because I don't want this video to be 2 hours. I'm going to keep it down to my typical hour and a half. That should be only an hour. That's okay. All right, here we go. Moving on to integrals right here. So integrals of parametric curves. We can do derivatives. We should be able to do integrals as well. So all we want to do is just update a couple of our terms very, very similarly to how we updated our differential terms for our derivatives. So all we're going to do is start with what we're comfortable with and just rewrite some terms here. So here's our scenario. And by the way, I just have to say it every single time because otherwise the calculus police are going to come and just straight up abduct me. dy dx is not a fraction, and it is not necessarily appropriate for you to ever treat it like a fraction. It looks like a fraction, and that notation was decided upon by people that recognize that it often, but not always, follows same rules as fractions follow. But it is very important that you recognize that dy dx is one quantity. We chose notation that matches fraction notation because it is often the case that they are the same, but it is not. And so if you ever want to be considered a smart person by other people that are good at math, then you will always acknowledge that dy dx is not just a fraction with a numerator and a denominator. It is a single quantity. That being said, often it works out algebraically to be equivalent to treating it like a fraction. You guys will see in Calc 3, you'll see a bunch of good scenarios in which it does not pan out for and I mean, again, the whole fraction math I'm talking about is like this right here. Like this is literally how algebraic fractions would simplify is down to this. That's a bit more of a coincidence of calculus than the fact that these are algebraic fractions right here. Yes, exactly. You need to literally be told it's a fraction. Yeah, coffee gopher. It's never truly fully trust that, but let your intuition suggest that to you all the time. It's always a good guess, but just be aware that smart people know that it's not always the case. So don't overdo the whole fractiony idea here, but I'm going to abuse the crap out of it in this line right here, and I'm going to be right about that, so it's okay. So now that I've gotten our addenda out of the way right there, our typical integrals are just like this, right? This is like the most generic integral I could ever write, the integral from a to b of f of x dx. Here, it's going to be more useful for me, and by the way, I really don't want that formation because f is doing a different job for me today than that. So this is really our more appropriate formation here. An integral says add up, that's the integral sign, says add up all of the heights, the y values, times all of the infinitely thin widths, the dx values, and do that for all x values from a to b. That's going to accumulate for us an area overall, right? So it's good to think about y's as heights. Heights times infinitely thin widths, that's our Riemann sticks that we're adding up areas of. If you add up an infinite number of Riemann sticks infinitely close together, then you will get a total area having been accrued. So all I'm going to do is take this formation right there and make a couple quick substitutions. Y is our heights. Y we know we're describing parametrically as g of t. So one substitution is y is just going to get swapped out for g of t. The other swap I need to make is dx. So what do I do with dx? Well, I'm thinking to myself, I'm going to go to my really generic, bland, pointless statement right there. Dx dt equals dx dt. Because I have the deep confidence that in this scenario, my derivatives are equivalent to being treated as fractions, but that's not always true. I am going to head and do a light bit of fraction math right there, which really is basically just me thinking of this as saying, just go ahead and multiply that dt term to the other side. I'm going to say it just one more time and then I promise I'll stop. It's not what happened. I didn't multiply by a dt, but it does turn out that in this scenario, thinking of these as fractions is equivalent to their calculus interpretation. So therefore, this is the swap that I can use to rewrite my dx differential term in terms of a dt differential term. And the only included term that we're going to get, this is really more of like a chain rule term that we're popping out here, is the derivative of our x stuff with respect to t, which we can do. The derivative of x with respect to t, since x is f of t, that's just f prime of t. So this is basically my two variable substitutions that I'm doing. I have an integral with a y and a dx, and I want everything in terms of t. So y is now g of t, dx is now f prime of t dt. And now we've got everything in terms of t, we got integrals. The only other light difference that we want to distinguish between here is that a and b should be more indicated as alpha and beta right here because they are general points in space. A and b are x values. Alpha and beta are xy ordered pairs. There are starting and our ending locations there. And so here are g, and so we've just substituted the terms. Y became g of t, dx became f prime of t dt. And so now we've got our new formation right here. This doesn't look like super straightforward. It doesn't look like something that's easy to remember, but I think that both of these substitutions are easy to remember. So this is one of those ones, this is on the long list of things that I straight up never remember this formula. But if you were to say to me, Tony, you have 5 minutes to come up with the integral of the area underneath the parametric curve, I'd be like, and then I would just write down these two lines right here and I'd be done. It's not really that bad. So I think remembering these substitutions is much easier than even remembering this formation. Or at least for me it is. And you can decide that for yourself right there. So, Coffee Gopher, you're asking the good question right there. He says, why not have our bounds represent the t parameter? And part of the reason is because it's more often the case that we know the locations rather than the t values that result in the locations. Exactly, from t equals 0 to t equals 10. And you can see it, that's basically what we did right here, right? We were really given the location information of 3, 0, and we had to stop and do the work to get the t information that was associated with the xy information so that we could use the t information with our derivative. We're going to want to do something like that down here. And what I'm going to show you is that the reason why it's slightly better to use the points as your references rather than your t as your references is because you're going to make the same small mistake that I made. And I'm going to go ahead and make that mistake right now. And that will allow us to come back and answer your question. It's really just a little bit of a bookkeeping thing where I keep on accidentally getting something backwards. And it's because I keep on doing things in terms of t instead of in terms of a and b, or alpha and beta, I should say. So let's do this example. And in the example, you're going to see that we're going to get our answer wrong. And the answer is wrong because I'm trying to force myself into t when I should probably leave this as alpha and beta. So here's our basic thing right here. We're going to do a bland example as we generally do, which is to say, we don't trust this equation. Anytime you get anything new, you should say, no way, I don't believe you. And then you should prove to yourself that it's true by doing an equation, doing a computation to which you already know the answer. So let's use the parametric equations to find the area of a circle. So we know if r equals, and let's just do this with the radius 1. I don't need extra weird stuff here to make this more difficult for myself. Then area equals pi r squared equals just pi times 1 squared equals just pi. So we know that this is our desired answer for this final result out here. All right. So let's go ahead and set up some parametric equations to represent a circle. Let's set up some integral expressions to represent the area. And let's go ahead and compute it and see if we actually do get this guy right here. So parameterization of a circle. We did this last class, and what we really saw was that there's actually lots of choices for the parameterization of a circle. The bottom line is, as long as one of them's cosine and one of them's sine, and the coefficient out front is the radius, notice that this is 1 times cosine because we have a radius of 1, then we should be good to go. So let's stop real quick though. I'm setting up one of the many parameterizations of a circle. There's lots of them. There's 4 of them because we could have cosine and sine, we could have sine and cosine, and positive and negative on either of them don't matter either because all we have to verify is that our x squared plus our y squared is going to give us sine squared plus cosine squared, which it will in all those cases. So really, there's 4 acceptable parameterizations of a circle. And in fact, even more than that, because then we could also talk about putting negatives and stuff and other speeds inside of our inside right here. So lots of ways to parameterize a circle. So what I want to just do real quick is stop and think to myself, what is this circle actually going to look like right here? And in which direction are we parameterizing it? If I take t to be equal to 0, then that's going to give me x, y equals. If I plug in t here, 0 is going to give me 1, and y is going to be 0. So this is our t0 location. And I'm going to try and do a smart thing right here. What I'm going to think to myself is, let's just go up to the top right there and just find the area of a quarter circle, and then we'll multiply our answer by 4, and we're going to expect to get pi once we multiply by 4. So I'm thinking to myself, if I go to t equals pi halves, since I know that t is really measuring angle here, then that's going to be giving me my xy location of 0, 1. And so this is going to be what I'm going to refer to as my final location right here. So I'm going to kind of think of this as my parameterization, and this is sort of like my alpha location and my beta location in my mind. That this starts at this t equals 0 and t to pi halves right there, according to the parameterization that I have selected. Right. So what we want to do here is we want to set up our, and I'm going to need some room because we're going to see that I'm going to get a mistake in here. So let's come back to our formation right here. I've got, oh man, by the way, this is we're calling this our f of t, and we're calling this our g of t. I want to keep these guys straight right here for our integral. So this should be our integral from alpha to beta of g of t, f prime of t, dt. So I'm going to say it's 4 times a quarter circle's area, right? We're just going to do the first quadrant stuff, multiply by 4 to get our thing. So that 4 isn't part of our integral expression. That 4 comes from the geometry of this problem in symmetry. So what do we have here? G of t, f prime of t. All right, let's do the dang thing here. So I'm going to not worry about my bounds at all. Let's deal with the integration, and then we'll manage our bounds and our coefficient of 4 here. So what do we actually have going on inside of this thing? G of t is just sine of t. That's my heights. That's my y values. F prime of t, that's our derivative of cosine. That should be negative sine of t dt. So we've already got our integral expression. We're good to go here. We've subbed in the parts that we need. All right. So let's go ahead and see if we can evaluate this thing. And again, I'm going to try and not worry about the alpha and beta for right now. It looks like I can pull this negative out front right here, and we're going to get a sine squared of t dt. So if I can integrate sine squared, I'm good to go. Unfortunately, when I think about my trig associations with sine squared, the first thing I think of is 1 minus cosine squared, but that's not helpful because it just replaced one squared trig with another squared trig. My next thought to myself is it would be really cool if there was like times cosine of t in here, because then I could do u as sine, and then my du would be handled, and I just get the integral of u squared. I don't have either of those things, but I do know that there is one other trig replacement that I could do here, which is that sine squared of theta is 1/2 1 minus cosine of 2 theta. That's one of our trig identities, I think, that we get right there. Exactly. Double angle formula is going to get that guy for us. And by the way, let me check my notes here. Did I get the right... is that a plus or a minus in there? I always remember that formula, but I never remember if I'm supposed to do the addition or the subtraction in there. Where the heck did my problem go? Yeah, 1 minus cosine 2 theta, right? So that's going to be the substitution that I'm going to use here. This is going to get us from a squared thing that we can't handle because it requires chain rule to a single, or a chain rule that we can handle right there, right? It's just a constant multiple of 2. So here's what I'm seeing. I'm going to replace this sine squared with 1/2. So this 1/2 is going to join up with the 4 that's sitting out front. And that's going to make this -2 times the integral from alpha to beta. I've already used up the 1/2. So this should now just be 1 minus cosine of 2t dt, right? The 1/2 coefficient joined with the 4 coefficient to make a 2 coefficient sitting out there. Now I can take the integral of this guy right here, right? -2. Now we're going to get the integral of 1 is t minus the integral of negative cosine. So I know that the integral of cosine should just be sine. So I'm going to get minus sine of 2t. But if I were to take the derivative of sine of 2t, I'd get cosine 2t times 2. I need to undo that multiplication by 2 that's going to pop out. So I'm going to get a 1/2 that's going to sit on that guy right there. And we're going to evaluate this guy from alpha to beta. So I'm still kind of hanging on to what are we doing with this alpha and this beta right here, right? Now, we are thinking to ourselves that alpha is our starting point. T equals 0. We are thinking that beta is our ending point. T equals pi halves. So maybe those are acceptable. So let's go ahead and throw those in here. And we're going to see, we're going to get an ever so slightly wrong answer for a reason that we'll be able to identify. And we'll come back and we'll fix it. It's going to be pretty easy. So here's what I'm seeing here. I'm gonna write this here then as t equals pi halves to t equals 0 right there. Right? That's going to be my actual bounds that I'm going to evaluate this guy at. So what do we get? We're going to get -2 times pi halves minus 1/2 sine of pi, because that was 2 times pi halves, minus 0 minus 1/2 sine of 0. And notice that what I'm getting for my answer right here, notice that this is equal to 0, this is equal to 0, this is equal to 0. So all I'm getting here is just these parts, which is giving me, and the obvious question, right? We knew to expect, yeah, there you go, call coffee gopher. You get your hours of staring at that trig sheet. It's funny how you learn these things for stupid reasons, right? So what happened here? We thought we knew the answer to be pi, and I just did all this work, and I'm convinced that we're onto something because I sort of got pi, except I picked up a negative. Why did I pick up a negative right here? So the reason why we got a negative here is because what we really just did is we just integrated not from like, and now, by the way, make a distinction here. I'm about to say A's and B's, not alpha and beta. Yeah, we could just drop the negative and call it a day. That's what I did when I took Calc 1, 2, and 3 for sure. Yeah, just erase it and put a check mark next to it is the obvious move. But let's see why here so that we can set ourselves up to not have to do that in the future. I've done plenty of that. So again, alpha and beta are beginning and ending points in space. That's different than when we typically refer to integrals from A to B, which are typically x locations on the x-axis. What we know is that when you integrate, and I'm going to try and do all my hand motions backwards so it matches the movement here, that when you go from A to B, you are accumulating things with positive delta x's, and so you get positive areas. But when you do the integral from B to A, when you work backwards, you get the negative of the integral from A to B, and that's because your delta x is the negative of what it used to be because you're going in the backwards direction. Notice that in this case, we accidentally set up our parameterization to work from right to left instead of from left to right. We started with our starting location being the rightmost, and we ended with our ending location being the leftmost. So this says to me, we did accumulate our areas from right to left. If we think about this as a traditional integral, our delta x term was negative. And so we should have had heights times negative widths, which should give us then negative values right there. So this is really just us saying, this is just our integral identity. The integral from a to b of something is the negative of the integral from b to a of something. We did a right to left integral here just by nature of our parameterization. And so therefore so I'm like joking about just erasing the negative and calling it a day. But in a sense right here, I'm saying, okay, I agree with that because here I accumulated my area in the negative direction and I got the negative of the answer I expected. If we would have accumulated our area in the positive direction, then we would have gotten the correct positive answer that we would have expected right here. So this is just to say to you, you should recognize that regardless of what we think of as alpha and beta, as far as starting and ending points, that's sort of our interpretation of it. We still kind of always want to pick alpha and beta to be our leftmost and our rightmost points, so that we are still accumulating areas from left to right and still getting the correct signs that are going to be associated with these here. So let me just say this, and I'll just type this out. We got the negative of the correct answer because our alpha starting location, and I'm going to put that in quotes for starting, was to the right of the end of beta, the ending location. Come on. Beta, the end. Right? And so what I'm saying here with this statement is just that we know our general integral properties that the integral from a to b of f of x dx is equal to the negative of the integral from b to a of f of x dx with a less than b. And that's all that happened right here, right? We just went from right to left, so we got the negative of the right answer. And so this is to say our lesson here is let alpha be, get out of here. Wait, what? How did that happen? All right. So regardless of what you think about your starting and your ending endpoints right there, to have delta x be positive, we always got to go from left to right, basically. And so another thing that we could have said here is maybe to just have used a different parameterization. You should notice, by the way, that if we would just swap cosine and sine in our parameterization, then we would have been going from the top of the unit circle down to the side over there, and we would have been naturally arranged to be from left to right there. So maybe it's that our parameterization maybe should have been different, x being sine and y being cosine. That would have naturally fixed the problem for us here. And anyway, I'm not going to go back and like redo this. I'm just saying we got the negative of the correct answer, but that's just because we sort of accidentally integrated from right to left instead of from left to right. So it's just a thing to like be aware of. And I could even go so far as to say like, man, even if you like on a test question sort of got to exactly this and then said to me, oops, I know that the answer should have been positive. It looks like I got the negative because I switched my bounds of integration. Then you've said to me everything that I want to know that you need to know. And so I'm good with that kind of stuff. So you should set these up the correct ordering out there. But like, if you get a negative, you should know why. That we got the flipped scenario right there. All right. So let's look at an arc length example, and this will be my last full example for the day. After arc length, we will do an example. And what I'm going to say is that surface area is going to follow the exact same updates as we'll have seen from the arc length thing. There's nothing exciting new that's happening with surface area. You can do it. You still need to get into dx dt and dy dt from dy dx, but there's, I don't know, even the book is like, oh, and we get surface area too. And I agree with their statement of like, there's nothing new and exciting. The arc length one is pretty cool. And if you like the algebra that we've already done, then you're going to like this algebra even more. And I've got a pretty cool example problem set up for us here as well. So let's hit arc length. And then we'll see, oh yeah, surface area. I can see how that'll work. So arc length and parametric curves. Again, we just need to swap out some differentials is all I'm going to say here. So, so let's do our little derivation here. With y equals f of x, back in our original arc length scenario, we came up with this integral right here. We said it was the integral from a to b of the square root of 1 plus dy dx squared dx. There was another formulation in terms of dy. Let's just handle our dx one right here. We can do them both the exact same way. There would be no essential difference here. So hopefully you can see right away that we have two pieces that we've already managed to deal with before. I already know how to make both of these swaps, right? I know that dy dx is dy dt dx dt. And I know that dx we've replaced before as dx dt dt. Right? I know these two swaps. So let's go ahead and do this then. We need to make a big square root here because I've got now a gigantic term underneath here. And dx I am going to write as dx dt dt, right? So all we want to do is just clean this up into a usable form. I've made my substitutions. I've got everything in terms of the t's that we want to see, but there's some really nice convenient stuff that's going to happen here. So what I'm going to do here is I'm going to be picturing this as sort of like a 1 plus a squared over b squared, and I'm going to factor out a 1 over b squared, and that's going to leave me with b squared plus a squared. This is going to be my algebraic maneuver that I'm going to do over here right now. So I'm looking at factoring out a quantity of 1 over the denominator of the second term. But importantly, we're also underneath the square root right here. So what this is going to look like is this. I'm going to factor out from this thing a 1 over dx dt squared. What that's going to leave me with inside of the square root, since I'm dividing out a dx dt squared from 1, that means it has now 1 whole dx dt squared. I have also divided out the denominator dx dt squared from dy dt dx dt squared. So this should just be a dy dt squared. And we still have our dx dt floating on the outside. And you should notice that the square root of a square, we can just pop that outside. Inside, we get these pretty convenient expressions right here, dx dt squared plus dy dt squared. And notice, what do we have outside the parentheses? Well, we have a dx dt, and we have a 1 over dx dt. Those cancel perfectly. That was pretty freaking cool. Oops, we got to upgrade those to alpha and beta now again. This is just going to leave me with dx dt squared plus dy dt squared. So I think that this is a really cool derivation right here also, that we factor out that 1 over dx dt squared, and it perfectly cancels with the dx dt that we got from swapping out our differential terms. So we made two substitutions and they combined very nicely. So like honestly, is this even any harder than our original arc length formula? I have to say basically no. Like it's okay, so we have to compute two derivatives, but like did not get that much more difficult. I think this is a really cool derivation that happens right here. So we start with the 1 plus dy dx squared. We write dy dx in terms of the parameterization. We write dx in terms of its alternate differential dx dt dt. And notice here, it's sort of like the dt's just multiply and cancel, leaving us with the dx. We factored out the denominator squared. The denominator squared under the square root is just factoring out the denominator, and the denominator then cancels with the additional dx dt that we had on the end. And since we factored out the denominator from 1, we get a copy of it, and we factored out the denominator, so it's just gone from the other part right there. So pretty cool derivation. So this is our arc length formula here. So let's go ahead and use it, and let's find what I think is an interesting arc length right here. So here, and by the way, I want to kind of motivate this here. I shouted at you guys in the last 2 weeks a couple times. After taking this class, you can take both Calc 3 and differential equations. They're both very different classes that are both very dependent on everything that you've learned in this class and in Calc 1. Calc 3, I like to think of as basically just Calc 1 with an extra dimension. It says, let's do all this stuff in 3D, and let's see that some of the things work out the same. And that's convenient as in Calc 1, but we're going to see some things don't work out the same as in Calc 1 because the extra dimension kind of funks things up a little bit. And that's just the cool part of Calc 3, is seeing what's the same and what's different. Calc 3 is very cool. It's very spatial. It's a lot about getting comfortable with 3D objects and describing them with curves and computing volume surface areas, but with different integral setups. Differential equations, on the other hand, the one that I'm teaching next semester, the one that you're all going to be taking with me next semester, is where we solve equations with derivatives in them. And how do you solve equations with derivatives in them? Well, we undo derivatives with integration often. And so the reason why we need to be epically good at integration for differential equations is because we're trying to undo derivatives to solve equations that have derivatives in them, often using integration. What's going to end up happening in that semester is we're going to get just tons and tons of different solutions to differential equations, and then we're going to attempt to analyze them. And one very common form of solution to differential equations, especially when we look at lots of our physics problems next semester, we're going to see general solutions that look like this kind of a lot, actually. So what is this really describing to us? So I just want to say to you, I'm picking this example specifically because this is exactly a solution that you're going to see many times when you take DiffEq with me next semester. So this isn't just me making stuff up right here. This is very specifically describing a very simple physical scenario right here. So how about it? This is a damped harmonic oscillators solution right here. So some physics words being thrown in there for you. So what you should be seeing here is this. You should first glance at this parameterization and say, I feel like this looks something like a circle. And the reason I'm thinking circle is because my x stuff has cosine, my y stuff has sine. I know that if each of my two trig functions are in each of x and y, regardless of which one is in which, regardless of positives and negatives, we're talking circle stuff. It might be that we're going forwards, going backwards, going fast, going slow, different starting locations. Those all might change, but the shape will be a circle, right? So I'm picturing circle stuff. But what I'm seeing here is there's this coefficient out front. Now, what you know about coefficients out front of cosine and sine is that you should typically be thinking of this as like r cosine theta, r sine theta. This seems to me like e to the negative t is sitting in the radius slot. This looks to me like the parameterization of a circle, but we have e to the negative t in the radius slot. So what should the shape end up looking like? The shape should sort of look like a circle, but the radius should be decaying exponentially. So what's the name of the shape that's sort of like a circle, except where the radius is always getting smaller? Well, let's go ask Desmos to graph it for us. So our equations were, I gave you the equations where x was. By the way, can I do this? Can I do it this way? And by the way, don't look at these graphs. These aren't going to be helpful for you until next semester. Can I just do... Is it cool with me doing that? Apparently not. So that's kind of disappointing right there. I was hoping it was just going to let me throw those in there. I think it's only okay with like f of x, g of x, stuff like that. I don't think it's down with you naming a function x or y in here. So it doesn't look like that's okay. Oh well, that's okay. We tried. So let's go back to doing it in our ordered pair form here. E to the negative t sine of t. So my claim to you was that our shape was going to be like a circle, except where the radius decays over time. And what I'm going to do to help you see this is I'm going to make a slower decay rate. It's only going to decay 1/10 as slowly to help us visualize this guy right here. And let's go ahead and extend our time. So I'm going to start the time at 0, and I'm going to just let the time get bigger and bigger until I think I've seen what I want to see. And by the way, notice another thing that I know about this shape. Its maximum x and y values are like 1 and -1. So it's got to be contained within a box, like a 1-unit box or 2-unit box, technically, right there. So what happens? A circle with a constantly decaying radius. It's a spiral, right? It's a circle where over time your radius gets smaller and smaller and smaller. So it's really just a spiral, right? But how far down does the spiral go? Well, it should be the case that you can just keep on looking closer and closer. Don't throw up by looking at the screen. And we should just be able to keep on going, and the radius should just keep on decaying and keep on decaying and keep on decaying out there, right? So on the one hand, this curve looks really long, but you should be recognizing that right now, like we're talking about lengths that are like 0.000005 units long is like how long this distance is right now, right? So in a sense, there's an infinite amount of spiral here, but it's also the case that this infinite amount of spiral is all contained within this little box that lives right here, right? So I'm going to just chop these back off just because I want my calculus to be easier. This is still a spiral, but it's, right? And here our spiral is decaying in one direction, but not the other. Here now we're back to being a spiral. This is a much more extreme spiral because it's decaying in radius much quicker, but you can see we're still doing this action where we're in a sense decaying towards the origin right here with our radius, right? So it's still spiraling, but it's spiraling much, much quicker. The slow decay in radius gives us the more visually satisfying spirals. This one's just like, it's hooking in there. It's decaying really quickly. So we know our idea of what this thing looks like. And by the way, notice this is all the arc length that I can see from 0 time to 1,000 units of time because it just decayed to a very small radius very quickly right there. So what I want to know is this. Can we compute the entire length of the forwards time spiral defined by this parameterization right here? And when I say the entire length of the forwards time spiral, I just mean all of our positive time. So when I use this weird language on purpose just because I want you guys to think about forwards time and backwards time. Time 0 is our initial time. Forwards time is all positive times. Negative times are all backwards times. You can think about moving backwards through time. Obviously a little bit weird, but like, I don't know, you've all seen like a rewind of a video before, like picture the particle undoing its motion, stuff like this. So this says t is greater than or equal to 0. Find the entire length of this thing. So let's go ahead and see if we can do it here. So we've got our formula for arc length here. I don't really know how to phrase beta. Okay, I guess I sort of do. We can figure out where we start and where we end right here, where alpha and beta should be. And we've got our formula right here. So let me give myself my page that's going to take to do this. And let's see if we can do it. So our arc length should be the integral from alpha to beta of the square root of dx dt squared. You know, the other thing I really like about formulas like this is you don't even have to remember orderings here because addition can happen in either order. So it's not like you have to like remember one before the other or something like that. Like it's just, you just throw the pieces in there. Alpha at time 0, what are we seeing? I'm seeing that x, oops, let's write that as an actual y. Xy is, if I plug in 0 into these equations here, 0 gives me 1 for cosine and 1 for e. So I'm going to get 1 as my starting location. 0 into sine gives me 0. So we are starting at on the x-axis at 1, 0. But what's up with beta? I guess this is going to be like time equals infinity right here. And you should notice that what's going to happen here is as we get infinitely large values for t, our radius is going to have decayed down to essentially 0 in both of these cases right here. So we should be ending up at the origin. And I know that by taking my limits of my negative exponential functions there. But in any event, these times are more likely what we're going to want to use as our bounds right here. All right, so let's go ahead and compute our dx dt and our dy dt that we need. I'll keep this scrolled up so we can see them. So here, x of t was e to the negative t cosine t. So dx dt, I'm first going to take my derivative of the exponential. I'm going to leave my cosine of t alone, plus I'm going to leave my exponential alone, and I'm going to take the derivative of cosine. That's going to give me negative sine. And so I might write this guy as, let's see here, if I factor out an e to the negative, yeah, sure, let's just factor it out this way here. And in fact, no, I think I'm going to factor out a negative e to the negative t. Notice this grouping is negative and this grouping is negative, so I factor out the negative and the e to the negative t, and all I'm getting here is just a cosine t plus sine t. Again, there was one negative in this group, I factored it out. There was one negative in this group, I factored it out, so the resulting parts were all positive here. The only difference here is for our next one, we're getting sine of t. So can I squeeze it onto the bottom of the screen? Yes. And for dy dt, we're going to take the derivative of e to the negative t. We're going to leave sine of t alone. Plus, we're going to leave e to the negative t alone. We're going to take the derivative of sine of t. Here, I think I only want to factor out a positive e to the negative t. I've got a positive cosine term here, but I do have a negative on the cosine grouping over here. As you might imagine, this formula isn't too bad to state, but it can easily often be the case that this square root just makes things non-integrable. So it's not clear that we're going to be able to do this necessarily, but I think I can at least set this statement up and maybe make some statements about it here. So let's see what's going to happen. So I'm going to throw this stuff. I've got a big old square root expression that I want to make right now. It looks like we've got negative e to the negative t, cosine t plus sine t, all squared, plus e to the negative t. It's a positive e to the negative t, cosine t minus sine t, all that stuff squared. Okay, dt. That doesn't look nice. Oh yeah, the golden ratio totally does that spirally based thing there, and it's for a similar reason based on their relationship to imaginary numbers. We'll see that next semester also. See you next semester. So let's see if we can do anything with this guy here. The thing that I'm seeing is really nice is this is at least products that are being squared, so I can apply the squarings directly. So I think what I'm seeing here is an integral from alpha to beta of big old square root here. Here's what I'm noticing. There is a squared, so I guess I'm just going to square negative e to the negative t. That's going to give me e to the negative 2t cosine t plus sine t squared, plus, again, I'm going to get an e to the negative 2t. Notice here the negative down here got squared away. There's not one to get squared away on this. These just match now as coefficients. This is cosine t minus sine t squared. And I'm kind of thinking this might work out because the thing that I'm seeing here is, one, I can factor out e to the negative 2t. E to the negative 2t is the same thing as e to the negative t squared, right? That's the same thing. So I'm going to get this e to the negative t now. Oops. Outside of the square root. What do we have going on inside of the square root? Well, inside of the square root, I'm going to multiply these out. The other reason I'm feeling pretty good about this is because I know that sine or squares of sums of sine and cosine all condense down to just being 1. The other thing I know is that this is x plus y squared and x minus y squared. I think their cross product terms are going to be the same but opposite signs and are going to cancel out. That's going to be nice here. So what are we going to get? I'm going to get a cosine squared t plus 2 cos t sine t plus sine squared t. That's our first grouping. That's this stuff. The e to the negative 2t's has already been pulled out to be an e to the negative 1t. My next grouping here, hold on, I gotta fix this. I've got a random blop right here. There we go. That is a positive right there. That is not a negative. Our next grouping here is plus. I've got cosine squared t. I've got a minus 2 cos t sine t. And on the end, I have a positive sine squared. And the great news here is that that term and that term cancel. And it looks like I have two positive cosine squareds and two positive sine squareds. I'm adding up sine squared plus cosine squared. I think I'm going to be in really good shape here. So now where are we at? Integral alpha beta of e to the negative t. I am really just looking at here 2 times cosine squared t plus sine squared t, right? I did a little bit of factoring right there, but I don't think it was too crazy. I think that was an easy algebra step. I had 2 copies of cosine squared. I had 2 copies of sine squared, all added up. I factored out the 2 part of the copies, and we know that this is literally just 1. All this entire square root turned out to be just e to the negative t times root 2. And that was it. That worked out freaking nicer than we could have expected. Holy cow. Alpha, beta. It looks like this is just root 2 e to the negative t. That's all we're getting for the arc length of this spiral right here, which is super cool. So I can do my integration, but I'm thinking now that, again, alpha should be t equals 0. Beta should be the limit as t goes to infinity out here, right, is how we want to kind of use those ideas. So what I'm seeing here is root 2. This should be negative root 2 e to the negative t is what I get from the integral, because it just pops out a negative, and that's the only thing I have to worry about. And I'm going to evaluate this from t equals 0 to t equals, and let's just call it b right here. And I'm going to go back and fix this the same way we typically do. I'm going to do this properly, since I think the last time I wrote an indefinite integral, I was bad with my notation here. Limit as b goes to infinity is what we're getting here. So it looks like this is going to be, out of here, surface area. Nobody wants to do surface area. All right, so it looks like I'm just seeing here that negative root 2 pops out front, and this is just the limit as b goes to infinity of e to the negative b minus e to the negative 0. You should notice that this is just equal to 1. And what happens when we let b go to positive infinity for e to the negative b? What you should be picturing here is that e to the negative x looks like this. So it looks like as x goes to positive infinity, this gets closer and closer to 0. This is like 1 over e to the infinity power. That's 1 over infinity. That's going to tend towards 0 right there. So what I'm going to get here for my answer then is negative, okay, I did that right, negative root 2 times 0 minus 1. And that's going to give me root 2. And that is just crazy to me. How simple is that? That's a very, very satisfying answer, in my opinion, right here. That was a super cool problem that worked out like kind of surprisingly well right there. So realize that sometimes these things, and again, I think the lesson today is the lesson that's been the same in a lot of cases, which is just try some stuff. I know it looks gross. Maybe it's going to be nice. You should trust that trig stuff often works out much nicer than we think it's going to right here. So another really weird thing here, and this is, you can kind of go back and forth on this. I could see how you could be in agreement with this or not in agreement with this. I'm traversing a spiral for infinite time, and over an infinite amount of time, the distance I traveled is just the square root of 2. That seems kind of strange to me. On the other hand, I kind of have a sense in which I can believe this, because I know that that entire spiral was just trapped inside of a box that went from -1 to 1 and -1 to 1 right there, right? It wasn't possible for us to leave that box right there. And so, gosh, just looking at this, it's like it's kind of a tough sell in a sense. But I don't know. I mean, can we believe, like right now, like what you see on the screen is the box from like -1 to 1, right? Or pretty dang close to it right here. I guess I could believe that this length is root 2. We're hardly accruing any length. I mean, I think the other good thing to picture right here is this. Let's play this game right here as my kind of like wrap up right here. E to the negative a cosine of a. What I want to know, the question I'm trying to answer right now is, how far along this curve do we need to get before I can't even see any change in where A is anymore? That's really me saying, where's like the first 99% of our length being accumulated at? And the reason I think this is a good question to ask is because I know that with my radius decaying exponentially, I expect my length accumulation to die off exponentially here. I'm going to set this to be from 0 to, I don't know how far I need to go here. But if I go too far, it's going to make my steps weird here. So let's do something like that. So notice over here, you should be able to see that I am certainly starting at our claimed initial position right there. Let's go ahead and make this red. I think that might be better here. Again, shout at me for any colors if that's more helpful to you. And so I don't want to necessarily click play on this. I want to drag this myself so I can see. So the thing I'm seeing here is it only takes about 1.5 seconds, or I might be inclined to think maybe like pi halves seconds for us to get through like literally most of our length right there, right? And if we wanted to go a little bit further, I could say it looks like I get to literally all of the parts of this that I can see within like the first 5 seconds. For all of the rest of time, for the remaining infinite amount of time, and by the way, if you are looking like ever so carefully at the dot right there, you could see it doing a little dance right here because it is doing more spiraling out there. But it's very, very, very hard to detect because we're not zoomed in far enough. But you should notice again that if I zoom in far enough, or I guess I got to make this go further here. I can make this go further, and I can make this go further. Then we could keep on zooming in. And if we zoom in far enough, what you're seeing is that that red dot doesn't seem so close anymore, right? It now seems far, but recognize how short of a distance is that we're additionally accumulating right here. So I also do think that one of the interesting things might be to say, for how long does it take for us to accumulate the first 90% of the distance of our trajectory? Well, all we'd have to do is find 90% of the square root of 2, and then find out how much time it takes to elapse just that arc length. And what I think we'd end up finding is an answer that's, about like right here or something like that, right? There's the first 90% of our arc length is probably accumulated in the first like 2 seconds. And the remaining 10% takes infinite time for us to accrue right there. Yeah, totally. Good call right there. Zelprod saying some people draw a right triangle to show what a root 2 length is. Some people draw a spiral right there. So I like that. I, I'm vaguely assuming that you're joking, but I have to assume that even if you're not, that there's plenty of mathematicians on Earth that are like, yeah, see, told you, square root of 2. It's that length right there. Weird ways to come up with expressions for known quantities right there, right? Which is another thing that people like to do in math is to say, oh, by the way, did you know that pi could also be represented as blah, 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 blah? So other cool stuff to see right there. So that's kind of my wrap up right here. And again, I think this is a super cool problem. As I kind of said, basically I'm going to say, I don't think I need to talk about surface area. What we know is that our surface area, come on, scroll with me, is that our surface area equation was just like 2 pi r times arc length. Well, we already got our arc length stuff. So it's really just going to be like 2 pi, and this is going to be like your, I guess when we were doing our surface area things, if we revolve, rotate about x-axis. So if we rotate about the x-axis, then we're rotating this way. So our radius is our vertical measurement, it's our y. So this would just be 2 pi y dy dt squared plus dx dt squared dt. And then we say for y, we say, oh, that's our y is our g of t statement right there or something. Or we could say, or it's our f of t if we rotate about the y-axis. So the exciting part about surface area is that it uses arc length in its computation. Since we just did arc length, we have everything we need to know about surface area. So I'll probably hit you guys with the surface area question, but I don't think there's any like broad concept that you'll need to like get over that's associated with that. Since the definition of our surface area formula literally is mainly just about multiplying circumference by arc length, we've already worked out how arc length is new. all we literally do is just change y to our parametric equation, or our parametric equation for x if we're going about our rotating about the y-axis instead. So I don't think surface area is exciting enough to justify me dragging this video out for 30 more minutes, which is why I'm going to stop right here. You should obviously read the example at the end of the section where they do a surface area computation with parametric equations. And in my opinion, it works out like I expect it to right there. I don't think there's the new exciting stuff is there. I think the new exciting stuff is getting these kind of pretty cool things right here. And again, what I really want to end with is always, every day for the rest of the semester, is my pitch to you that you should be taking Math 55 differential equations with me next semester. We're going to see that this is going to be a pretty typical type of result for a solution to a differential equation in two variables, which we're going to solve a ton of next semester out there. So this isn't just some problem I'm making up. You should be saying to yourself, when in the hell do we ever see exponentials times trig functions? Oh man, if that's the question that you're asking, then boy, do I have a class for you. So happy week 10, everybody. And maybe, as I always do, I always think that I just have one parting announcement. There's always seven. As you can see above my head, what we're talking next week is sections 10.3 and 10.4. We're going to talk about calculus in polar form. We already know polar. We don't really need to introduce that in the same way we needed to introduce parametric stuff. So we will kind of start right away in 10.3. Okay, 10.3 is like a polar coordinates day, but it's like we already know polar coordinates, so I'm going to skip kind of a lot of that stuff. 10.4 is really where the hot action is going to be, and 10.4 is going to be a very similar day to today, where we're saying, hey, listen, you already know how to do areas and arc lengths in other formats. Let's do areas and arc lengths in polar. So hopefully next week is a nice little sort of like, I don't want to say like a soft week, but like a soft-ish week right there. The other thing I do want to say as my final comment is I am looking for us to take a test, partly because our remaining unit of chapter 11 is different than everything else that we've really talked about here. So I do want to sort of separate that material out. However, we're obviously not going to take a test until I have finally finished actually grading our current tests, which I am going to wrap up grading like today and tomorrow, I think, and get those back to you guys. And so we're obviously not going to take another test until we've gotten this one back. And I've been taking forever, partly because I've planned my time wrong, partly because my computer is driving me insane. I should be getting a new computer in the mail tomorrow, but that doesn't help me for grading these tests since I want to have them graded before I spend all Wednesday and Thursday setting up my new computer. But anyway, the point is, I think we're going to do a lightly modified test relative to the last one there. I think I'm going to give you something that's going to be a little bit shorter than the previous test or something like that. But the point is, I think that we're going to like kind of work out what we're going to do for the tests 2 weeks from now. On the schedule I had made for myself, it said we're going to next week do polar and the test, because really the two sections of polar we can easily cover in one day, one video, and the test would be the other half of the week right there. I instead think that next week I'm going to do 10.3 and 10.4 on Monday. That means I'm going to start chapter 11 on Tuesday's video next week. And then the following week, in week 12, is when we'll take a version of a test that's associated with our more recent material here, and then carry on with chapter 11 stuff. So look for there to be a test type item in week 12, but I would like to tamp it down a little bit, basically, is all that's going to happen. I want this to be a lower stress thing. If you can do the MyOpen math, and if you can really do the homework, and if you can actually show me the work for these things, then I know that you can do the content in this class. Forcing you to try and do it in some time constraint and then just creating a bunch of grading for me that's not necessarily additional reflection of what you know doesn't really benefit anybody, I don't think. So we're going to take another test in like 2 weeks, but I think it'll be slightly milder maybe than the previous one. I don't think the previous one was too bad, but still. Anyway, that's out there on the horizon. So next week we'll hit polar, and we'll hit our introduction to chapter 11 type things there. Hey, Kiwi Gamer, nice to have you here. So we'll look into that stuff there next week, and I will see you guys then. Happy week 11. Hit me up at the Zoom office hours. Hit me up by email if you guys got any questions. Otherwise, I will see you guys next week.